So far we have discussed about discrete systems which were deterministic in nature. That means, with respect to time, with respect to a particular interval, we are knowing the value of the variable to be somewhat exact. Only in the last few classes, when we were talking about quantization error, rounding of error, we talked about noise which were random in nature. So, random signals are defined in terms of their statistical properties. Now, they are not periodic. But their statistics will give you some properties. You cannot take Fourier transform or Z transform of random signals, all right, but you can take Fourier transform, that is in the frequency domain. You can describe some of the statistical properties like autocorrelation, covariance and so on, because these properties are, again we will show later on, they can be also expressed in terms of the time variable or in terms of discrete variable n, all right. So, suppose you have a speech signal, we speak a word, we utter different sounds. So, they are all random in nature, all right. When you say B, there is a particular signal which is basically a sample of so many so many sounds that we make, all right. A, B, C, D, and B may be pronounced by different people in different ways. So, there are so many possible sounds, so many possible signals, all right, out of which when we utter, say when I utter a particular sound B, then it is one of those ensemble of those signals which is the sound B. Okay. Even the same person, when he utters the same sound at two different instant of time, suppose I have got cold, all right, today I may have a little nasal sound, so the signal will change. So, it is random in nature. There are so many instances of randomness in signals that it is a very important study to be made. We are not going to the details of random signals, just basic statistical properties we are going to discuss. So, let me first take up. So, speech signal is a random signal. Let me define some of the simple quantities. P x alpha we define as the probability that the variable x is less than or equal to alpha, all right. P x alpha we define as the probability of the variable x. X is a random variable, x is less than equal to alpha. We define actually the probability in terms of a density function, okay, which is small p, we write alpha, which is variation of this probability with alpha. Any question? Why should it be a partial derivative? It is implicit, it may be a variable of time also, okay, though we are not mentioning it here in a situation when this varies with other variables like time, then it should be partial derivative. So, for a continuous variable x, we can write p x alpha as minus infinity to plus infinity small p x. Okay, I will write u du. Okay. This is alpha, this is minus infinity to alpha. The value of p x at infinity will be minus infinity to plus infinity p x u du. That is the maximum probability that you can have, and that is equal to 1. And p x minus infinity will be from minus infinity to minus infinity, so it will be 0. So, p x alpha will be varying between 0 and 1 as alpha changes from minus infinity to plus infinity. Next, we define the rth moment. The rth moment as mu r, okay, is equal to expected value of x to the power r. Let me put this bracket. X is the variable, random variable to the power r. So, this will be defined as minus infinity to plus infinity, covering the entire range alpha to the power r p x alpha d alpha. Okay. This is a running variable alpha. R is any positive integer. So, when we talk about random variables, they are defined in terms of the statistics. By that we mean all the moments. So, the 0th order statistics will be r is equal to 0. If you put alpha equal to 0, it gives me only the total probability. All right. If I take alpha equal to 1, sorry, r is equal to 1, so that will be the mean. That is, if p x is equal to 1, p x is constant, then it is the normal arithmetic mean. So, it is basically p x gives you the weightage. All right. So, weighted mean, that is known as the mean. So, mean we write as expected value of x. Okay. So, there are three quantities: the first moment, second moment, and mean of the squared quantity, squared variable. These are the three quantities which define more or less the statistics of a random variable. You can go for higher order statistics also, higher order moments, but for most of the practical situations we deal with the mean, variance, and the mean squared variable. Okay. So, this we write as mx is equal to minus infinity to plus infinity alpha p x alpha d alpha. Mean of the square and we define variance as expected value of x minus mx. Okay. That is expected value of x minus expected value of x. So, square of this, I will put another bracket. Okay. So, square this. And what will be this? Minus infinity to plus infinity. Say if we take the running variable alpha, mx squared px alpha d alpha. Okay. I have a very bad habit writing infinity and alpha more or less with the same symbol. This is infinity and this is alpha. Okay. The limits are minus infinity to plus infinity. So, sigma x squared, if you expand this, you will get sigma x squared as expected value of x square minus mx squared. Okay. And sigma x we call standard deviation. Okay. Now, this is very important whenever there is a particular distribution given, say distribution of marks, we talk in terms of the dispersion sigma x, all right. How much is the variable changing, in which range it is changing and how is it distributed. You can have the range similar, all right. Suppose the performance of students in a particular class, there may be two subjects where in one case the dispersion is high, that is the distribution of marks may be like this, in this is the mean value, around the mean value. In the other case, and suppose the range is only up to this, in the other case like this, both of them are bell shaped, having same range, same mean value, but the distribution is different. So, here sigma is more, all right. This sigma 2 is more than sigma 1, from the nature of the characteristics you can find out. Suppose a random variable, we will take a simple example, a random variable has a probability density function given as px alpha equal to 1 minus alpha by 2 for 0 alpha 2 and equal to 0 otherwise. Okay. What is the nature of this function? What is the nature of this function? It will be a straight line like this. So, this is the random variable x and this is the PDF. Now, let us compute the three quantities, the first moment, second moment and the variance. What will be the first moment? Could you check? That is mx. Okay. What is the probability Px alpha to alpha. What is the dependence of this with respect to x? That is, this is the density function given. So, what is the probability? Probability means area under the curve from minus infinity to that point. From minus infinity to this 0, it is all 0. So, you have to take only in this area, and at x, what is that capital P x? It will be only this area. So, can I write in terms of that variable x? So, we are writing this as alpha. So, it will be P x say du, okay, which will be 1 minus u by 2 du integrated from minus infinity to plus alpha. Okay. Is it all right? So, it will be alpha minus alpha squared by 4. Is it okay? I am just taking u as the running variable, all right. So, alpha minus alpha squared by 4, so 0 alpha. So, at alpha equal to 0, it is 0, it is okay. The area is increasing and maybe somewhat like this. I do not know, that you have to compute. It will be like this, okay, or maybe like this. You have to check up, you have to plot this. What will be the probability that this lies between say 0.6 and say 1.2? What is the probability? This is the density function given. What is the probability that x lies between 0.6 and 1.2? So, just I can write P x alpha 1 minus P x alpha 2, where this is alpha 2, this is alpha 1. So, P x alpha 1 is this area, P x alpha 2 is this area. So, the probability that it lies between 0.6 and 1.2 is this, okay. I mean area under this. So, it will be 1.2 minus 1.2 squared by 4 minus 0.6 minus 0.6 squared by 4, all right. So, that gives me, correct me if it is all right. M x, what is the mean value of this distribution? So, 0 to 2 minus infinity to plus infinity will be now reduced to 0 to 2 alpha into 1 minus alpha by 2 d alpha, okay. Is that all right? The variable and this is the distribution. So, it is alpha squared by 2 minus alpha cube by 6, 0.6 to 1.2, sorry 0 to 2, we are not computing the earlier. So, 2 minus 8 by 6, that gives me 2 by 3. Okay. What is the expected value of the squared variable? Same? Okay. So, that also comes out as 2 by 3. All right. Now, let us compute the variance. So, it will be 2 by 3 minus 2 by 3 squared 4 by 9. So, it is 2 by 9. Okay. Quite often we come across a probability distribution function, probability density function, which is uniform. If you remember, we are seeing the quantization error. So, it may be say from A to B, range may be specified. All right. So, the density function can be written as 1 by B minus A when it is lying between A and B and equal to 0 otherwise. All right. What would be the average or the mean? It will be 1 by B minus A to B alpha d alpha. Okay. Is this all right? See, this is a probability density function which is constant. So, alpha into 1 by B minus alpha B minus A into d alpha. So, that 1 by B minus A I have taken out, that is B plus A by 2 alpha square by 2, and if you take the limits, then common factor B minus A goes out. What is expected value of x s squared? Again 1 by B minus A to B alpha squared d alpha. So, it will be B cube minus A cube by 3. So, B minus A will get cancelled. So, it will be B squared plus A squared plus AB by 3. Okay. So, what will be sigma x s squared? All right. So, you have computed for two typical distributions. One was a distribution like this, the other one is a distribution like this. Okay. Compute all these three for a probability distribution. Say minus 2 to plus 2. Okay. The area will be equal to 1. So, correspondingly you calculate the height 1 by 2. Okay. 1 by 2 half base into altitude, that will be the area. So, base is 4, half into 4 into height. So, height will be 1 by 2. So, once you know this, you can find out the equation of the line, and from there, sorry, this one, yes, thank you very much. All right. So, this one, so you can find out the equation of the lines, and hence you can compute all the three quantities, the integrations for different moments. Try this as an assignment. For two random variables, x and y, we study their joint statistical property in terms of the joint probability density function. They are of practical interest. Quite often we find signals which are either correlated or at least which are now whose properties are to be computed in a joint manner. So, suppose x is the variable which takes the values from minus infinity to alpha, and y is a variable which takes the value between minus infinity and beta. Then probability x y alpha beta is the probability that x is less than equal to alpha and y is less than equal to beta. Okay. In many books you will find random variables are written as capital X and capital Y. Okay. So, henceforth I will be using capital X and capital Y, and the joint probability density function is defined as the partial derivative with respect to alpha and beta. So, the probability p x y will be basically minus infinity to alpha minus infinity to beta alpha beta we should not have the running variable same as the limits. So, let me put it as u and v, okay, and this is a du dv. So, when you are considering the joint probability density function, normally this distribution, this density okay, and minus infinity to plus infinity for both the variables will be always equal to 1. Again the same slip, u and v should write du dv equal to 1. Anyway, it was not alpha, so I could have put alpha beta. P x y alpha beta is always less than equal to 1. So, the value of the total probability will be between 0 and 1. Minus infinity and minus infinity, it will be 0. Now, we define cross correlation between two variables x and y. Cross correlation correlation of x and y we define as expected value of x and y. Okay. Which is between minus infinity to plus infinity alpha beta p x y alpha beta d alpha d beta. That means you take the product of x and y at all possible values of alpha beta and then take their average. Expected value means basically average. So, similarly, gamma xy is equal to expected value of x minus mx and y minus my. Okay. That is minus infinity to plus infinity alpha minus mx into beta minus my d alpha into the probability p x y alpha beta d alpha d beta. Is it all right? Sorry. Equal to phi x y minus m x y. All right. I phi x y, did we not define it? Yes, phi x y was expected value of x y. So, it will be like this. The variables x and y are linearly independent or uncorrelated if you find expected value of x y is equal to expected value of x into expected value of y. Okay. What is expected value of x y? Is phi x y, all right. And what is expected value of x? M x, m y. So, if phi x y is equal to m x into m y, that means this will be 0. Okay. That is gamma x y is equal to 0. So, if gamma x y equal to 0, then they are linearly independent or uncorrelated. All right. Quite often we try to find out if there is any correlation between two signals. Suppose there is a random signal, a noise for example, a random noise. When you try to find out the correlation of a random noise with any other signal, it is always equal to 0. That means they are two independent variables. They are statistically independent if p x y alpha beta is equal to p x alpha into p x beta. So, it can be shown that if x and y are statistically independent, then they are also linearly independent. the reverse is not necessarily true. If x and y are statistically independent, then they are linearly independent. Converse is not always true. I leave it as an exercise. Okay, try to prove, if not the second one, at least the first one. So, if they are statistically independent, if x and y are statistically independent, it is easier to derive the statistical characteristics. Suppose x and y are statistically independent variables with mx and my as their means, then the variable v is equal to ax plus by. Ax plus by is another random variable. It will have mean as, say, mv will be a times mx plus b times my. Can you prove it? So, what will be mean of v? What will be the mean of v?
Mean of x plus b1. Expectation of x plus b1.
Expectation of ax plus by. Okay. Since they are statistically independent, so expectation of, so a times mx plus b times my. Sigma v squared, what will be the variance of the variable v? This is precisely you calculate when there is a mixture of, say, sinusoids. You talk in terms of the RMS value. RMS value, when you compute, it is the RMS value of the first component, square it, multiply by the square of the weightage. Similarly, RMS value of the second quantity, square it, plus multiply by the weightage, and so on, and then take the under root of the entire sum. You get the RMS value of the overall variable. When it is a mixture of, say, 2-3 sinusoids, you compute the RMS value in a similar fashion. Now, let us take a problem. Suppose we have Pxy is equal to a, the range of alpha and beta is given like this, that is alpha, if you write alpha it is between -1 and +1, and if I write beta in the alpha beta plane, I am just showing the variables, it is between 0 and 1. Okay. So, this is the range of alpha and beta. Alpha and beta will be this set of points. Determine the and equal to 0 otherwise. Okay. So, the probability density function is, if I take an alpha beta plane and if the height represents the probability density function, then it is A, all right. It is like a rectangular cake, no, just a brick. So, it is equal to A, it is uniform for all the points of alpha and beta, the range is specified, and it is equal to 0 otherwise, say in this side it is all 0. What is the value of A? Okay, very good. So, what is the total area? 2. 2 multiplied by A is the total volume, all right, and that is equal to 1. That is good. So, A is equal to half, all right. If you go by that integration relation, it is between -1 and +1, and between 0 and 1, A d alpha d beta, that PDF is A, and that is equal to 2A, all right, and that should be equal to 1, total probability. Therefore, A is equal to half. So, compute the probability Pxy x lying between 0.5 and 1, okay, y lying between 0 and 0.5, all right. So, what would be the value? 0.5 and 1. So, once again A is between 0.5 and 1, and B is between 0 and 0.5, 0 and 0.5. So, it is this small rectangular piece into A, is not, into A, height is A. So, this is 0.5 and this is also 0.5, okay, 0 to 0.5, I am sorry, y is between 0 to 0.5. So, 0.5 into 0.5, 0.25 into A. So, the total probability will be 0.25 into A, that is 0.125. Okay. That is the volume of the brick. For a discrete signal, we write the mean as expected value of x n. Let me put once again the first bracket. So, that is minus infinity to plus infinity, okay. Yes, please. In the discrete domain, we will put summation, all right. So, expected value of x n, how do you put that? Now, in the beginning itself I had mentioned about the speech signal, all right. We are taking discrete domain of time, all right, but we are considering at any moment there can be so many possibilities, all right. At any moment there are so many possible values, all right. So, it is one of those values. what is the probability that at this moment the say sound will be like this, what are the possible values of the sound. Okay. So, it is in the discrete domain of time, is it all right? We are not varying n at any instant of time n, what are the possible combinations, what are the possible values of x n. So, it will be minus infinity to plus infinity, this is a range of x at any instant of time, alpha p x n alpha n d alpha. Actually, we are in the habit of taking mean with respect to time, all right, not the mean at a particular instant of all the possible values of that variable at a particular instant. If that mean is same as the other mean, then it is definitely a stationary process, it is an ergodic process, all right. So, expected value of x n squared will be minus infinity to plus infinity alpha squared p x n alpha n d alpha. If you want to calculate for all possible times, then only the summation comes. I am not summating over n, it is integrated over alpha. So, variance will be expected value of x n minus m x n, all right, squared. After using the third bracket so often, I am used to it, so I have forgotten about the first bracket. That is equal to expected value of x n squared minus m x n squared. Now, mean, variance and the squared value, mean squared value, mean of the squared value, these are functions of n, is it not? That means, they can change with time. So, if a process does not have a constant value, that means does not have a value which is independent of n, then it is not a stationary process. When it remains constant with respect to n, then it is a stationary process. We call it strictly stationary process if all other moments, higher order moments are also remaining stationary, that means they are constant, they are not changing with n. Okay. So, when we say, when you speak, for example, in a speech signal, when I make a sound, for some time you will find it is having a particular average, particular variance, then I change the word, I mean I change the sound, all right, I switch over to another sound, then again the mean changes. So, it is a constantly changing mean, variance and other moments. Okay. For a complex sequence, we write x n x real n plus j times x imaginary n. Okay. So, mean of this will be expected value of x real n plus j times expected value of x imaginary n. Okay. So, you segregate the real and imaginary parts in terms of the means. Similarly, variance we will find expected value of x n minus m x n magnitude squared, and when you take magnitude squared you will get expected value of x n magnitude squared minus m x n magnitude squared. Okay, actually it is immaterial, you need not put a bracket. You can expand and then see for yourself. X you put here and then see. Sometimes we are interested in the statistical relation between two quantities in the time domain, or that means at two different instants, how are they related, x at this moment, y at the other moment, or x at this moment and x at the other moment. So, when we are talking about the two different instances x and y, they are cross correlations of a different time span, all right. When they are with the same variable, then they are autocorrelation. So, these are two important quantities. Now, depending on the nature of variation of these with respect to the time span, the time range, if we can express them, and if the statistical properties are definite, then we can take their Fourier transform, all right. So, you can take transforms not of the original signal, but their properties. Original signals x and y, it will be difficult to take transforms, but if you take their autocorrelation or cross correlation, you can take their transforms, all right. So, this is one very important property. I do not think we will be able to take up any example. We will take it up in tutorial classes a little more, in a little more detail about the transforms and other relations if time permits. Okay. Let us take a simple example. A cosine omega naught n plus phi. The probability distribution of this amplitude is say 1 by 4 and is equal to 0 otherwise. Okay. Similarly, for this phase phi, we have 1 by 2 pi and 0. This is between beta is between 0 and 2 pi equal to 0 otherwise. That means, the phase difference can vary between 0 and 2 pi, okay, and the magnitude can vary between 0 and 4. So, what would be the statistical properties of this? So, P A, the joint probability density function will be 1 by 4 into 1 by 2 pi. Okay. So, 1 by 8 pi in the range this 0, alpha, 4, 0, beta, 2 pi, okay, and equal to 0 otherwise. All right. It is a constant. So, you can calculate mxn, xn, x is this, all right. So, it is having dependence on two random variables a and phi. So, what is the what is the average value of this? What is the mean? One by 8 pi, 0 to 4, 0 to 2 pi, then the variables a and phi will write as a running variable alpha and beta. So, alpha cosine omega naught n plus beta d alpha d beta. So, if you complete this, I leave it as an exercise, you complete this integration, it will be 0, two sinusoidal quantities, all right, separated by 2 pi. Similarly, you also compute expected value of x squared, all right. You work it out, find out the value. And then autocorrelation, okay. If I take an autocorrelation of lag m and n, there are two variables, is not a and phi, magnitude and phase. So, there are two variables m and n. I am just giving you the result, check up whether you are getting this, all right. So, autocorrelation of two variables means in both m and n you can take two dimensional transforms. Autocorrelation of one dimension you can always take one dimensional transform. Okay. So, we will stop here for today, we will take up some problems in the tutorial class. Thank you very much.